program, and I'll introduce the three speakers individually before they start their presentations. For those of you who don't know DASH, DASH is short for Data Science Center in Health, and this is aimed at embedding data science in the DNA of the UMCG. The vision of DASH is for UMCG to be an international leader in data-driven healthcare innovation. Why? Data-driven innovation contributes to our goal of building the future of health and has the potential to transform healthcare and health itself. The DASH program focuses on a number of facilities and activities, as you see here. They are quite diverse, and I strongly recommend you to get to know better what DASH can mean for you and for your research. I'm part of 4 DASH experts in different areas of data science, and my personal expertise area is in clinical cohort data. And this has a strong link to the topic of this afternoon's webinar. So let's get started with the webinar of today. First of all, can I ask you to mute your microphone? We will do first all 3 the presentations, and after that there will be time for all your questions and for some discussion. Regarding your questions, you can either put them in the chat, or at the end of the presentations, you can raise your hand below in the bar below the presentations, and then you can speak and unmute when we give you the floor. So without further ado, I will introduce the first speaker and we'll get ready to go with this exciting topic. This webinar will be recorded, so you will be able to review this afterwards as well. The first presenter is Dr. Gert-Jan Pelgrim, and he's a postdoctoral researcher of the Radiology Department of the University Medical Center Groningen. And in this presentation, an overview of the B3CARE project will be given. B3CARE has to do with early detection of the big 3 diseases, as Gert-Jan will explain to you in a moment. Gert-Jan will explain what has been done so far in the project and which steps are still to be taken. Gert-Jan, the floor is yours.
Thank you, Rozemarijn. Thank you for the introduction. I will share my screen. Yes. You can see my screen, right?
Yes.
Okay, great. Okay, yeah, again, thank you for your introduction, Rozemarijn. As Rozemarijn explained or already introduced, I'm Gert-Jan Pelgrim. I studied technical medicine. I did my PhD here at the Radiology Department, and now I'm working as a postdoc data manager in that same department on the B3CARE project. And I'm excited to talk about this B3CARE project for you today. In this presentation, I will talk about the B3CARE project, like I said, and first I will discuss the outline of the project. There are some different work packages I will discuss. What infrastructure do we already have, and what did we make, and what data can we use, and a bit about the industry partners we have. First, I want to show a background movie about the B3CARE project because that gives a nice overview of the project as a whole. So, so I think this movie gives a great overview and well, does a better job at explaining this in a short time than I could do. So that's why I added this. So the overall idea of this project is to advance the technology readiness level of the integrated B3 care screening. So the B3, the big three diseases of the future: lung cancer, cardiovascular disease, and chronic obstructive pulmonary disease, or COPD. And those techniques, we want to use AI and AR tools to advance these techniques in the near future. So what are we then looking at? The big three diseases: cardiovascular disease. Here you see a CT scan, the right lung, left lung, and the heart, and we see a calcium spot here in one of the coronary arteries. We can see a higher amount of calcium in more diseased arteries. So that's an indication of increased disease. For instance, for lung cancer, we can see here a lung nodule in the left lung. And yeah, we also looking at techniques to do this automatically, to look at to use an AI to determine those nodules automatically and to detect them automatically. For COPD, you can see here an example of COPD. I don't know how good this project in this presentation, but you can see that there's normal lung tissue in the bottom half of the lungs, and here you see destructed lung tissue with only air and no breathing capabilities anymore. And those things you want to detect early in order to treat it better. So when we get to the work packages in battery care, there are several. First, we wanted to create a secure work environment, a secure data environment where we can store the image data and also do measurements and get measurements back. So that's what we do in work package 1. Then with work package 2 and 3, with work package 2, we look at reference values for those imaging biomarkers. We do a data extraction of, or we look at the scans. We determine lung nodules. How many lung nodules does a normal person of 50 have? Or you could look at several tasks or things we do in the big three diseases. So, for instance, how much calcium has a normal person of 50 have without smoking history and stuff like that. When we then we could then also store that back, and we can look at the reference values we create then in work package 2. When we do a manual reading, we have that gold standard reading, and we can check that and we compare that to a AI reading which is done automatically. If that AI is correct, then quite often it's faster and cheaper to use just an AI for that same purpose instead of a human who is often time consuming and it's laborsome work, which is also a high cost. Those measured biomarkers then also go back into the database, and we create a big database with which we can track all those results. The reference values we have created can also be used for our own machine learning purposes. For instance, for lung nodules, we have segmentations, or our calcium scores, we have segmentations of the calcium. We could feed those into a new machine learning projects and try and get better machine learning of or algorithms which could do that purpose. For instance, Ivan is now working on who's going to present later on the bronchial wall thickness algorithm, which uses this same purpose. And what we can do with that is those new algorithms can be then transferred or used in work package 3 as well to validate against the measurements we did beforehand. Now, once we established working pipelines, we could also check those for cost effectiveness and use those newly validated biomarkers in order to increase the clinical effectiveness and to try and to estimate how effective these techniques would be in future screening. And of course, it's of the utmost importance to not only keep this knowledge for yourself, because we gain a lot of knowledge by doing this, and I think it's really important to also share this with others, and therefore there's also a training and educational step that's been developed, and a course for instance for radiologists is in development. So one of the packages was work package 1, and in this work package we created a secure research environment, and I'm now going to demonstrate this. First we need to log into that research environment. In this case I have 2, but we can go into a VRW workspace. Once I click this, I get into this workspace. Here you can see all different kinds of programs which are in the workspace. For now, I use a couple, but there's also SPSS and R and Python. We are using RTank to save our PACS to save our imaging data. I now have one of the participants of ImaLive in here. That's a study we have been doing. And here you see the data of this participant, which we have in this database. Now, well, I'm just selecting a certain type of scan, and we can send it to a couple of DICOM modalities. And here you see AI solutions which we have within our research environment. One of them is PixelShine. It is a noise reduction AI, and there's a Siemens AI, and in the near future we will add a couple of other AIs to this in a way that we can send data there, and we will get back the reworked AI data. And then after that we can view this data in our software. This is the single via. It's a Siemens software which we use to view this image data. Here you see a normal CT scan of one of our participants. And then we can just do a normal reading of that CT scan. But we also have, I've sent this one by example for a calcium score evaluation, and you can see it contours the heart. And in this case, there was a really small calcium spot here in the LAD, one of the coronaries. And this is automatically detected by the AI and then feed back to our system. And we can check that within, well, another viewing purpose. One other AI which we have at this moment is the PixelShine, which I briefly talked about, a noise reduction software. And here you can see on the left side is the normal scan, and on the right side is the PixelShine processed scan. And you can see that there's a clear noise reduction in that scan. And they also claim that there's no distortion of any other tissues or any of the important stuff. And that's something we can test in the near future as well. Does it aid in detection of AI or of a human reader for instance, for calcium scoring or nodule reading purposes? So this is a short overview of what we have in the research environment at this moment. And there are going to be new projects added. So what data do we use at the moment? ImaLive is one of the main studies in there, in which we scanned 40 participants of lifelines 45 years and older. We did 12,000 low-dose thoracic scans to look for those the big 3 diseases: lung nodules, calcium score, and COPD. And well, and the COPD is also bronchial wall thickness, which is Ivan is going to talk about. So here, COPD, the bronchial wall thickness, the calcium in the heart, and nodules. So what's the status of that study? We now have gold standard measurements for 12,000 volumetry for 12,000 participants, all of them. Calcium scoring is done for roughly 9,000 and emphysema as well. So yeah, we're not there yet, but we're getting a long way. So there are also some add-ons to that study. Nelson B3 is a comparison study between the Netherlands and China, also for a low-dose CT scan, also in the research environment. Possibly we're going to add early synergy, in which we do an MR scan in high calcium score participants of EMALife. Then there's MemoLife, in which an MR of the brain will be done in participants with a really low 0 score and a high calcium score to check for differences in the brain. Then there's BioLife. That's a study for the sniffer tool to check whether that could aid in detecting cancer in participants with a repeat scan, which go for a repeat scan in our study. And well, the overall AI study for B3 care. So there are a couple of databases in there. So Rubinska, EMALife, then the China study, and Nelson, a thoracic study, and maybe we add early synergy in concrete in the future, but that's to be seen. There are a couple of partners in our study. So Siemens, who's we get single VIA and AI Red Companion from. TerraRecon will, in a really near future, enable the Envoy AI, and there you can link with a Docker your own AI, and that's what Ivan is going to use. I already showed a bit about PixelShine, and Quibim is going to present later today, and they have also a lot of AI solutions, and I'm really anxious to hear what they have to say as well. This is what I wanted to say. Thank you all for your attention.
Thank you very much, Gert-Jan, also for keeping in time. A lot of information is your time.
Yeah, I was a bit fast probably, but
let's keep the questions for later. But now I would like to continue with the second speaker, who is Ivan Dudrich. He's a PhD student at the radiology department at the UMCG, and he has an avid interest in applying AI to the clinical workflow. He's working on imaging biomarkers in the B3 Care project and specifically bronchial wall measurements. And in this lecture, he will share his experience with building a fully automated pipeline for bronchial parameter evaluation as part of B3 Care. Ivan, the floor is yours.
Thank you very much, Rozemarijn, and thanks, Gert-Jan, for your previous talk. Good afternoon, everyone. So as mentioned, my name is Ivan. I've trained as a medical doctor and I've worked in the hospital. And during my time there, I've gained an appreciation for things that speed up the clinical workflow and wanted to also see what I could do in this field. So I joined the B3 Care program, and now we're working on the bronchial parameter evaluation. So a brief overview of what I cover. So first, I will just explain what bronchial parameters are and why they are of interest to us. Then I will talk a bit about the project scope for developing an automated pipeline, and then some of the challenges that we came across and how we overcame them. So first, just a bit about bronchial parameters. Currently, we are evaluating their use as a CT scan marker for airway changes. So to understand why this could be possible, we need to talk a little bit about the pathophysiology of the airways. When the airways in the lungs undergo changes due to disease, they undergo things like inflammation and proliferation of goblet cells, which produces more mucus. They can also undergo epithelial changes, which results in their remodeling of the entire airway. So overall, this translates to imaging changes on CT that we can see and we can quantify. And this can be as bronchiectasis, where you have a dilation of the airway lumen. You can have thickening of the airway walls. You can have pruning of the airways, so just less airways overall visible. And you can also have things like mucus plugging, so blockages in the airways. And on the right image, you can see an example of thick airways on CT. So that you can appreciate the difference in the scale of thickening or changes that you can see. On the left at the top, you can see some normal bronchi on a CT scan with a nice thin wall with their accompanying vessels. And on the right in the top, you can see a somewhat thickened bronchi, and then at the bottom, much more thickened bronchi. So overall, all of these are different patients, potentially at different disease stages, potentially with different diseases. So bronchial parameters are there to try and summarize the overall state of the airway tree, and potentially could be used for things like quantification of disease or progression of disease. So to have a closer look at some of the potential parameters that we look at, the first question lies whether we look at individual branches, individual parts of the airway tree, or whether we look at it as a whole. And this can have some benefits. For example, you could have regional disease, and thus individual measurements in the area could be of much more benefit. Or you could look at a disease as a whole in the lung. And of course, in a research setting, we look at both. We look at combining both for evaluation of disease. So just to mention some of the commonly used parameters, when you look at individual measurements, you can focus on the lumen diameter. So that's the open tube of the airway. You could look at the wall itself and how thick it is, or how much of the total percentage of the cross-sectional area it occupies. You can look at things like the length of a branch, whether it's short, long, or whether it tapers down nicely, which would happen in a normal airway. Other things you can focus on are how many airways you can count in total, with less airways linked potentially with more severe disease. You could look at things like airway fractal dimension, so how complex the airway tree is, with more complexity potentially indicating a healthier tree. So all of these various things are still undergoing investigation, and that's why it's important to establish reference values and in such a database as we have with ImaLife. So because these bronchial parameters require essentially calculating a lot of different values in a lot of different places of the CT scan, this is extremely intensive work if you were to do it manually. So we focused on developing an automated pipeline to enable this process. We begin with just a standard, a low-dose CT scan, and we pre-process it so that it can be used in an artificial intelligence segmentation tool called a 3D unit. So it looks at patches of the CT scan and identifies where it sees airways. We then essentially make a segmentation, a 3D segmentation of the lumen of the airway tree, and we optimize that segmentation because the AI might not be the best at being extremely accurate with where the boundaries lie. It's really good at picking up small branches, and then we just optimize that to make sure that we get the most accurate measurements possible. So overall, the end result of this process is that we have an airway lumen and we have an airway wall, and from those two things, we can calculate all the bronchial parameters that we need. So I will briefly talk about how we the project scope, how we went about getting this to work, because we needed to combine a lot of different inputs, anonymized CT scans, low-dose CT scans, DICOM slices, things like that. It needed to be processed in a number of things. So using Python, using C++, using the GPU for AI, using the CPU for the optimal surface graph cut. So you have a complex interplay of a lot of different softwares, and all of them have to work in an automated fashion. All of them have to work and flag any faults because you want all of these things to be provided for the end for the end user. So one of the biggest things that helped with making the pipeline was to make a repository for it. And some of you may be familiar with this, some you may not, but there are repository tools like GitHub, GitLab, Bitbucket, and all of these allow you to basically trace the history of your code, whether you're working on it alone or in collaboration with someone. And as the quote here says, sometimes if you're working with someone, you can't tell what someone else might be working on until it's too late. And for us, it was a great benefit to collaborate with other individuals on the same code in a repository where we could trace the history. In a research setting, this also acts as your essentially your lab notebook, where you track where things go wrong, where things go right, and how to progress further. And here's just a snapshot of a visualization showing the complex file structure of the tool and a number of individuals working on the various files at the same time. So, as I mentioned, this tool needed to work with this GPU, the CPU. It needed to work in different environments with different hardwares, and thus it needed to be portable. For this, we decided to create a Docker image, and this is also going to work with the Eureka AI platform, as Gert-Jan previously mentioned. The Docker platform allows you to essentially package up complex softwares, complex codes, and either allow automation or interaction. So this greatly allowed us to test things out in a kind of packaged environment. So if things broke, they wouldn't break the rest of your code, they wouldn't break the rest of your machine. And it allowed for rapid prototyping and testing new changes, especially when debugging and when trying to figure out all the kinks in an automated tool path. So working on the code, we needed to also tackle some of the bugs and errors that came up, as well as at the end validate that our tool was actually performing well compared to current standards, and also whether we were getting realistic readings. So we had to tackle a few things with the data source. For example, some of the scan might be clipped, as in the lungs reach the edge of the scan area, and then segmentation may bleed into the surrounding area, and you have a lot of blobs and things like that where the AI doesn't really understand what this kind of leak means, whereas a human might be able to pick it up. Other times you might have disease in the scan, such as here you can see some cystic changes or some dilated things, and scrolling through the scan, we might be able to identify whether that's a cyst as a human, but as a AI, they might not necessarily be able to differentiate between the two. So we needed to flag these things. We needed to make sure that any time something like this pops up in an automated path, it would request a review. So all of those things require being familiar with the data set that you're working with what sort of things you can expect, and to foresee these issues and flag them as they come up. So after tackling all of these things, we needed to validate the tool. And in the ImaLive cohort, we have essentially a number of individuals that underwent a repeat scan, an average of about 3 months later. Such a short time span, it's thought to not really result in major differences in the airways. Thus, we directly compared the measured airways on their first scan to the measured airways on their second scan, and compared how close those measurements were. And we found that using our pipeline, we had moderate to good reproducibility for common bronchial parameters such as wall area percentage and luminal area. So these are commonly used in the literature to summarize airway measurements. And looking at a further analysis, we found that there's no systematic bias, and we had good limits of agreement between the first and second scan. So little variation between on the measurements between the first and second scan, showing us that we had reproducible results. And this, this automated pipeline wasn't just spitting out numbers that seemed right, but they were agreeing with previous scans. So our plan now that we have this pipeline is to process all 12,000 ImaLife scans using this AI platform with TerraRecon, using our packaged up Docker image, and we will build this data set of reference bronchial parameters for the population that we have, which is general population of the north of the Netherlands over the age of 45. And this will enable us to then further validate other AI tools to research into early disease and disease trajectory, and many other exciting things as well. So thank you all very much for your attention. And as what I mentioned, if you have questions, we will take them at the end, but you can also leave them in the chat for later. So thank you all very much.
Thanks much, Ivan, and very enlightening to see how you go about in developing such a pipeline based on machine learning approaches, and also the challenges that you faced in getting to your final product. Thank you. It's now my pleasure to introduce the third speaker. This is José Lozano from Spain, and he's joining us from the company Quibim. José is a data scientist at Quibim, and he has mainly worked on developing machine learning models to convert clinical information and imaging parameters into actionable predictions. And in this presentation, we will see the use of AI and image processing in building clinical decision systems, support systems in respiratory diseases. So basically the next step in machine learning products. So José, it's my pleasure, and the floor is yours.
Thank you very much for the presentation. Hi everyone, good afternoon. My name is José Lozano and I'm data scientist here in Quibim. Just to know, Quibim is a company that transforms imaging data into actionable predictions, designing tools to improve the patient outcomes. So as she said, in this webinar, I'm going to talk about the use of the AI and the image processing for the clinical decision support. So let's start. So this is the index that we are going to follow, and mainly I'm going to explain some projects that we have done in this context. So as an introduction, let's think on the application of biomarkers and companion diagnostics in general. A companion diagnostic is defined as a medical device that will identify patients before or during a treatment who are the most likely to benefit as a result of a treatment with a particular drug. So this test can be done based on genomics, liquid biopsies, pathology, or even imaging. And this is what helps advance the precision medicine. So the main applications of the clinical biomarkers and the companion diagnostics are mainly improve the knowledge of a certain disease related with the patient, try to identify the high-risk patients and the ones to most likely to respond, and also to allow a faster drug approval process, and trying to reduce the risks and the cost of the development. So in general, the main change is to link the images with clinical endpoints and the distinctive features of a disease. However, the application, the publications of large series to find surrogate imaging biomarkers for clinical endpoints or cancer hallmarks are scarce. So how to cross this chance? So in general, the creation of the AI models from radiomic features must follow a rigorous procedure. So we have to be very rigorous with the extraction of the quantitative features and biomarkers from the image. First of all, once we have an idea, we have to try it in a very preliminary environment. and small cohort with a small research project. Then, when we understand how the biomarker can be related with the endpoint, we have to think about the acquisition parameters of if the study can be done retrospectively. And additionally, the image processing is a quite important step because it's required to harmonize the image quality. And then we apply all the analysis tags and measurements. Once we are ready, we have to analyze the bias among the population with some proof of concepts, the proof of principle and the proof of efficacy, and against the expected clinical endpoints and hallmarks. And finally, if we succeed, we will create a structured report to interpret it by the specialists with the main results and the main information that we have obtained. So now I'm going to talk about some projects that we have done in Kivin related to this topic. The first one was for the idiopathic pulmonary fibrosis, the IPF, which is a chronic progressive and fibrosing intestinal pneumonia. The prognosis is generally quite poor, with a mean survival between 3 and 5 years. And it has other common disorders like the lung cancer or the pulmonary infections include too. So for these patients, an early identification and the treatment of these disorders plays a crucial role for the overall survival. We have in a study we enrolled more than 500 patients for further evaluation. However, after several exclusion criteria, of only 116 patients were retrained for the final investigation. 90 non-cancer cases and 26 lung cancer cases. So these cases were divided in two groups, one for the train with 92 cases and the validation cohort with 24 cases. In this study, all the CT images were transferred to the KVA platform, and a whole lung segmentation was performed automatically via deep learning algorithms with further 3D radiomics analysis and emphysema percentage evaluation. After some correlation analysis, we keep the most 26 important variables, and we found that the radiomics features show significant difference between non-cancer and cancer patients, especially the energy and the kurtosis values. A comparison between the IPF patients with and without lung cancer revealed an increased tendency to develop lung cancer with increasing values of the energy and the kurtosis. This table shows a comparison of the representative features between the cancer and non-cancer groups, where the energy and the kurtosis were the most relevant features. On the other hand, in the validation group, the combination of the radiomic features and traditional risk factors produced a diagnostic of 87 AUC, an accuracy of 75%, and we found that a similar prognostic performance between the radiomics features and the classical risk factors, as we can see in the comparison between the ROC curves, where for the energy and the kurtosis value, and the gender, the smoke, and the emphysema for classical risk factors. So in this study, we found that the whole lung CT texture analysis is a promising tool for the lung cancer risk stratification of IPF patients, and the combination of the selected radiomic features with the traditional risk factors such as sex, smoking, and percentage of emphysema can generate more accurate prognosis. Finally, All this information and the most relevant metrics were summarized in a report that can be easily evaluated by the clinicians to facilitate their decision. Another project that we have done was the Imaging COVID-19 initiative. This project was a multi-center European research project to develop a deep learning model for automatic detection and classification of COVID-19 on CT scans. This project was initiated by the European Society Medical Image Informatics, where 26 hospitals and 2 industry partners across Europe collaborated to develop these AI models. The industry partners were RoboVision and Kivin that participated in an internal hackathon to provide the best AI models for the COVID-19 diagnosis and the lung damage quantification. In this collaboration, more than 3,000 CT studies were collected and annotated by radiologists specialists in chest imaging. And the challenge consisted in 2 tasks: the segmentation task to train a model to automatically segment infection lens opacities, and the classification task to discriminate between 3 cases: the COVID-19, no infection, and other pulmonary infection. So the data collection started in March 2020 and ended in September 2020. And where we collected and matched all this clinical data. The annotation started in May 2020, where the participant hospitals labeled the image via the RoboVision platform, as we can see in the slide. And we performed the high-quality curation of the database, checking the image and the clinical data. Finally, the models were developed through this internal hackathon between Kivin and RoboVision. In the Kivin case, for the segmentation, we use a unique light architecture, and for the classification task, we develop a 3D convolutional neural network. Finally, the results are shown in the first table. So we can see Kivin obtained the best results in all the metrics with better dice score and intersection over the union, and lower false negatives and positives. Moreover, visually we can see how the Kivin segmentation was much precise than the RoboVision results, where the lesions were identified in a more precise way. Finally, the classification results show also better performance for the Kivin's models, with better AUC for all the different classes. So in this way, the Kivin algorithms and models were selected to the final report. Here we can see an example of the structured report where the most metrics are shown. The lung segmentation and the volumetric metrics for each lung are also shown, and in addition, we provide the classification probability for each class. With this report, the workflow of radiology can be much easier and so quick. So finally, other projects in which we are currently involved are the prediction of hyperprogressor patients treated with immunotherapy for lung cancer in a collaboration with Merck. Also, we have Chaimelion, a European Commission project to accelerate the lab market to transition for AI tools in different cancer types, including the lung cancer. And finally, an internal project in Kivin for the creation of a radiomic panel in lung cancer as a complement to the liquid biopsy and IHC. So that's all. Thank you very much. Now it's question time.
Thank you very much, Jose. It's a very interesting presentation, also showing the potential of using these kinds of new developments in the clinical setting also to predict disease and disease outcomes. I would like to ask all three speakers now to join us online. I kindly ask the audience if you'd like to have a question. I could imagine that you have questions. And I think it's a good time to take advantage of these experienced researchers in gathering the data, in developing a platform and a pipeline, and also implementing that in clinical practice. Please don't hesitate to put your questions either in the chat or put up your hand in the lower bar, and we'll give you the floor. I don't know if in the meantime, Gert-Jan and Ivan were also, yes, I see Gert-Jan and Ivan.
Yeah, thank you.
Great. So thank you all three for your very interesting presentation. So while the questions will start to come in, I would like to ask all three of you, what do you think at this moment would be the most, the strongest challenge to move forward with developing and implementing, particularly, I think those are two, of course, different issues, developing AI and machine learning and radiomics techniques, and on the other hand, the challenges regarding implementation. And maybe, Jose, can I start with you?
Yeah, of course. I think that now we are currently in a evidence generation mode. So we are trying to create different systems and applying into different organs. But these projects needs to be, the systematical reviews and the meta-analysis are needed. So studies, all these studies are good. We are in a good path, but studies, all these studies needs external validation at different institutions, and of course, all this consideration in the future go beyond oncology. It should be taken into account in other clinical scenarios too.
Thank you. Ivan, your perspective.
Yeah, so from my perspective, the current challenge lies, as I agree that one of the challenges is the validation, and that this is a very new field. And with technology, basically, it's not easy, but it's quick to develop a lot of different prototypes, a lot of different things that could potentially work. And the research is lagging behind because there's just not enough time at the moment. But to develop things as well, you need a lot of high quality data. For example, with AI, you need to typically train it on something, especially medical AI, like segmentations. And all of these things are very, these high quality annotations require expert use and expert time. And that's something that is just lacking in a lot of fields. So I think at the moment, those are the two main challenges in my perspective. Yeah.
Thanks. And Gert-Jan,
Yeah,
what do
I
you
fully
think
agree with that.
about this issue?
Yeah, I fully agree with both the previous comments. I think the problem is as well that what Ivan says is particularly true, but also that it's such a fast developing world, and we get new prototype versions every day, and then the old version is discarded, or is the performance the same as the old version? We tend to validate stuff that is generally a couple of years old, and then there's already a new version. How are we going to implement that and say, well, okay, this is good enough, we are going to start using it? But then the problem is, if you start using it, how do you decide on when to go on the next version? And I think that's a really difficult question to answer. How are we dealing with this? how good is good enough, and when to start over or get into the next step. That's I think really difficult to say for these AI topics.
Right,
And the
so
gold
if I
standard
can-
is difficult.
Right.
Oh, sorry.
Right. No, that I think also answers the first question in the chat. How far are we from implementation in clinical practice? So what you three mentioned are very important points. So that there's very fast development. So by the time you have validated one version, you have to already go to the next and start the whole process again. And on the other hand, the need for high quality reference data sets to be validating those new techniques and to gather enough evidence, as Jose says, to be able to indeed show in a larger setting that these tools have clinical value. And now maybe if I have time, I'll get back to you about that because I have a follow-up question on that. But first, I would like to turn to the chat because we have a couple of questions from the audience. One is, how far are the presented applications from the market? I think that's a question for Ivan and for Jose. Are they going to be available outside the hospital, for example, in a private clinic? So it's also a question of accessibility to the general public, not only to patients. And I think that's of course also an important question, is that recommendable? Ivan, what would be your answer to these questions?
For my perspective on them is that you can really you can turn a lot of these products into, well, a lot of these things into products already. However, I wouldn't be comfortable with using them without validation. The ones that we have, they are, for example, with my tool, they're purpose built for our data set and our use case, which is finding reference bronchial parameters. We work with open source tools as well. So in terms of accessibility to the general public and not only to patients, a lot of the kind of base of machine learning is open source. So you can find, various versions of the tools that are used. I don't think that's really accessible to the general public because it's still quite complex, and the outputs that you get might not necessarily be simple enough. You still probably need to have the clinical background or some sort of training to interpret these values. You will also, I think, one of the challenges with machine learning outputs is that, for the general public, there might be a perception that they are always correct or that they are absolute, whereas they typically work with probabilities. So there's still a lot of education to be done in the general public before they can be, before they should be openly available, I think. I might pass it on to the next if I'm taking too much time.
Jose, what would you say to these questions? What is your perspective?
Yeah, I totally agree with Ivan. I think the main challenge is the validation. Once the validation is done, turning this project into product have to pass certain regulations, also to be sure that the machine learning outputs are consistent. But the same words as Ivan said, really.
Thanks. And of course, AI software is seen as a medical device in EU regulations. So there's specific rules to obtain agreement from a European perspective to be using this in a clinical setting with safeguards for patients and any CT scan or imaging that you would use these on. I have also a question, I think, for you, Jose, because you showed different parameter sources. You showed that you use imaging data, but also clinical data. And the question is, are there possibilities to increase the probability scores by taking other parameters into account in a more integrated AI analysis?
Yeah, of course. In general, we have found that the use of imaging data with clinical data usually increase the results, and we obtain better results when we combine both type of information. So consider other clinical variables or new imaging features also can increase these scores.
And I think that's where we get into quite also an interpretation and ethical issue, because when you, for example, look at a lung nodule segmentation, a radiologist can check that it's correct or not. But if you start integrating all kinds of sources into a probability, it will be very difficult to have basically a kind of an ID if the outcome of the AI is more or less in line with what you think as a clinician. I think that's one of the challenges that we'll have. We're actually getting already very close to the end of this webinar. I think we could talk a lot more about this topic, but I would like to just ask you all three one very short question. I hope also for a very short answer is, what do you think in the next 5 to 10 years will be the value of AI in clinical imaging? What will be the main advantage? Jose, what would you answer?
I think the main advantage will be the accessibility for the decision taken for the clinicians.
Thanks. How about you, Gert-Jan?
Short answer. I think it should speed up the clinical process and the detection of certain things. Not all, but for mostly, I think that should speed up in the future.
Okay, and you, Ivan?
For me, I think it's going to have a great benefit to allowing imaging to be used as a screening platform in public health.
Thanks. Well, with this, I would like to heartily thank all three speakers for their very interesting talks that are really complementary and gives a broad overview of data set collection until clinical implementation of AI algorithms. For the audience, this webinar will be later also available online. And I would like to also announce to you the next webinar, which will already be in 2 weeks on October 5th. And the title will be, Do We Need Better Interfaces? And the registration is now open on the DASH website. Please check out the DASH website and social media to stay up to date, or feel also free to email us with any questions or suggestions. So with this, I would like to thank you all for your presence and for your active involvement, and I wish you a very good rest of the day.